Hi, my name is Nico Moritz from Mitsubishi Electric Research Laboratories, and I'm going to present our Interspeech paper with the title All-in-One Transformer, Unifying Speech Recognition, Audio Tagging, and Event Detection. And this is joint work with my colleagues Gordon Wichern, Takaki Hoi, and Jonathan LaRue. So the motivation for this work is that automatic speech recognition, acoustic event detection, and audio tagging are traditionally treated as separate problems with custom-made solutions. And this is in contrast to the human auditory system, for example, that uses a single binaural pathway to process sound signals from different sources. So investigating several questions in this work. One is, can we develop a system that moves closer to the versatility of the human auditory system? Another is, can training on multiple heterogeneous tasks lead to a single system with performance similar to or better than systems developed independently for each task? And can a single system successfully handle multiple tasks with widely varying characteristics, large length discrepancies, and with or without monotonicity? So, as an example, we look here on an acoustic scene of a home environment, for example. And let's say we had a microphone in that scene that was recording all the sound events that are happening here. And the corresponding audio clip is shown on top of this slide. The task of audio tagging is that we now like to detect the presence of certain sound events in that scene. For example, here we could detect that there was a cat meowing, there is speech, the baby crying, a dog is barking. We also have traffic sound coming from outside of the window, and we could also detect the acoustic scene itself, which is the home environment. So the difference to acoustic event detection is that for AED, we not only like to detect the presence of an acoustic event, but also their temporal alignments, which means we want to detect the start and the end time of each of these events. And now for automatic speech recognition, we want to ignore the non-speech sounds. And for the speech sounds, we want to generate a transcription. For example, here someone said, "It's your turn to change diapers," and another person was replying, "Okay, I do that." If we look at these problems from a technical perspective, there seems to be no real agreement on a common solution. As an example, we here look at different processing components used by the Decades Challenge baseline systems of different AT and ED tests from 2019. So even though they all aim at solving AT and AD tests just with different datasets, there's a wide range of different approaches that are being used. For example, they all use different sampling frequencies and feature extraction settings. There's a wide range of different neural network components that are used, as well as various methods for classification that are applied. And in fact, as far as we know, there's no model that has ever been proposed which can combine all the different audio processing tasks into a single system. Except there's one role model we all know of, which is the human auditory system. So let's have a brief look at the different processing steps of the human auditory pathway. So first, a sound signal that reaches the ears is going through a nonlinear processing of the loudness and also decomposed into a spectral component by the cochlea. After that, it reaches the cochlear nucleus, which distributes information to the superior olivary nucleus, which extracts cues for localization, for example, and to the inferior colliculus, which is responsive to amplitude modulation frequencies, pitch, as well as other spectrotemporal patterns. After that, there is the medial geniculate nucleus, which is like a relay station to the auditory cortex. And this is, for example, sensitive to intensity and duration of the sound stimulus, and it would also control the attention grid. So such processing is in many ways similar to an encoder-decoder neural network architecture, where the encoder would extract the important acoustic cues for a given task, the attention mechanism acts like the relay, and the decoder performs the perception for detecting and recognizing acoustic events. And now let's have a look at how an attention-based encoder-decoder neural network works. So in the beginning, we have an audio waveform that we use to extract acoustic features from it using a feature extraction module. And that acoustic feature sequence is input to an encoder neural network that does some further processing to output an encoder state sequence. And then we have a decoder neural network with an attention mechanism, and for attending to an input sequence, we require a query vector. And initially, that query vector is computed from a start token. In this example, it's this ASR token shown here. So we use that, generate a decoder state, which is used as the query to attend to the encoder state sequence. That can compute as a weight distribution over that encoder state sequence. This output then gets further processed by a decoder neural network, and from that we compute a new output token, which is hello in this example. And once we have that new output token, we can update the state of the decoder, use that new state vector to attend to the encoder state sequence again, do the same attention process as discussed before, and this will give us the next output token like word in this example. And we continue like that until we find the end of decoding symbol, which is the /s in this example. And this tells us that we can end the decoding process. So here we have an example for how we combine several different tasks into a single encoder-decoder neural network, where the decoder output is controlled by feeding a task-specific start token to it, from which it can compute the queries for the attention process, and which enables it to learn to separate between the different tasks. And here we show some more details about the architecture that we're using in our work. So we resample all recordings to 16 kilohertz, and we're using 80-dimensional log Mel spectral energies plus pitch information as the acoustic features. And the encoder neural network is based on a transformer architecture. Now, among the different tasks, the AAD task is special because it requires an estimate for the start and end times for each sound event. So this is why we split each event into 3 tokens, one for indicating that the start, one for indicating that an event continues, and one for detecting the end. However, encoder-decoder systems are not very suited for estimating specific temporal positions, and this is why we augment the transformer with a CTC objective function to promote a sequential ordering and also to learn the temporal alignments of each of these events. And this is shown on this slide here. And we use the CTC objective wherever we have a sequential ordering of events, and this is the case for the ASR task, and as discussed before, also for the acoustic event detection task. So here are the data sets that we're using for the study in this work. So for automatic speech recognition, we're using the Wall Street Journal corpus, which is read English newspapers. For acoustic event detection, we're using from the DCASE Challenge 2019 Task 4, the sound event detection in domestic environments task. And for auditing, we use 6 different data sets from various DCASE challenge tasks over the past years, ranging from scene classification, bird detection, and audio tagging in various conditions. And in addition, we're using the Ryerson Audio-Visual Database of Emotional Speech and Song, which is the REFDAS corpus, for detecting the emotion of a speaker, for example, whether a speaker is happy or sad. Then we can detect in this data set also whether a speaker is singing or just talking, and we could detect also the gender of a speaker. And this is the overall system architecture that we're using. We're calling this the all-in-one transformer model. So we have now one start token for indicating the ASR task, then one for indicating the AED task, and we have 7 different tokens to indicate the 7 different audio tagging tasks. So let's look at the audio tagging results. So where we use here micro average F1 scores for the evaluation metric, which means the higher the numbers, the better are the results. And for the baseline results, which are shown here, we use the official baseline system code that has been released for each particular task. This means that each of these systems was developed specifically for each dataset. Now here are the results for the for transformer-based systems that were trained for each single task individually. And as we can see, a transformer-based system can already outperform most of the baseline systems, except for test 1 of DK's 2019, which is the scene classification task, and where the baseline results are slightly better. So next, we're using all AT tests combined to train a single transformer model, and these results are shown here. And as we can see, for each individual task, the system's performance is further improved by such a multitask learning approach. And finally, here are the results for the all-in-one transformer model, which is trained for all the AT tasks as well as for ASR and AED combined. And as we can see, this is even further improving the overall system's performance in almost all cases. All right, so now let's look at the results for automatic speech recognition. We use word error rates to measure the system's performance, which means the lower the numbers, the better the system. So the baseline system here is the hybrid CTC transformer system that is just trained for ASR only. And you can see where we train when we train a system that can do both, so ASR and AED combined, we almost see no impact on word error rates for the WSJ benchmark. And also, when we train the all-in-one transformer system, so including the AT tasks, the ASR performance remains about the same. However, we actually would like to use such a system for recognizing speech in a complex acoustic scene, where we also have other non-speech sound events. This means we need to test the system's performance with regard to noise robustness. And for doing so, we took the clean test data of WSJ and mixed it with sound recordings from the demand and noisy datasets with an SNR of 10 dB. In this noisy test condition, the all-in-one transformer model demonstrates to be less noise robust compared to a pure ASR system, which can be explained by the fact that this system has learned to extract also information of non-speech sound events, while an ASR system typically would learn to ignore those or would never have learned to recognize those. So to enable the system to better separate between these different cues, we also investigated the influence of multi-condition training on the system's performance, and as we can see from these results, it substantially improves the noise robustness for both cases similarly. So it mostly solves the lack of noise robustness for the all-in-one transformer model compared to the pure ASR systems. Okay, here we have the results for the acoustic event detection task. The baseline system is from Dete's 2019 task 4, which is a system developed particularly for this dataset. And the numbers shown in this table are event-based and segment-based F1 scores, where again higher numbers are better. So we can see that the CTC transformer system is doing much less good for this task compared to the baseline. However, if we train the system for AED and ASR combined, the AED performance is getting significantly better. So the extra ASR training data helps to improve the performance of the AED task as well. And now for the all-in-one transformer model, we can see that specifically the segment-based F1 scores continue to improve, which means the system is becoming better in recognizing the acoustic events, but it has become less good in detecting the exact temporal positions, since the event-based F1 scores, which have a smaller tolerance towards misalignments, have gone down. And finally, here are the results for the all-in-one transformer, including multi-condition training, which further improve the results so that we can obtain better segment-based F1 scores to the development data set compared to the baseline system, and only slightly worse results for the test data set. So the conclusions of this work are that ASR, AD, and AT tasks can be unified under a single system architecture where model parameters are shared across all tasks. And multitask learning has shown to improve results for each individual task. And the all-in-one transformer model has achieved competitive or better results compared to all tested D-case challenge baseline systems, as well as to an ASR baseline system of similar architecture. And the proposed system can be used to perform the total transcription of an acoustic scene, which means it can be used to simultaneously transcribe speech as well as to detect the acoustic events occurring in such a scene. Thank you for listening, and goodbye.